Okay, imagine this. A doctor is trying to diagnose a really rare condition. They have this gut feeling they've seen a similar case before. But where? Buried somewhere in a digital archive of millions and millions of medical scans. Now, what if they had a kind of digital detective, an AI that could instantly sift through all those images and pull out the crucial clues? Well, that's exactly the promise of the new system we're going to break down today.
And this really gets to the heart of the problem. Every single day, hospitals are creating this absolute tidal wave of data: CT scans, MRIs, X-rays. For a person trying to find one visually similar case from the past in this, massive digital haystack, it's not just hard, it's pretty much impossible. And that's where this idea of a smart content-based image search comes into play.
The scale of this is just staggering. We really are talking about an ocean of images. And this isn't just about finding a place to store them, it's about being able to actually use them. If a doctor can't find relevant past cases to compare with a current patient's scan, then this huge well of diagnostic knowledge just sits there, completely untapped. Your typical search methods, like typing in keywords, they just don't cut it for visual data this complex. Here's a great way to think about it. It's like trying to find one very specific photo, not just any photo, from the combined camera rolls of every single person on the planet. You're not just searching for a picture of a dog. You're looking for a picture of a specific golden retriever with a little white spot over its left eye tilting its head in a particular way. In medicine, those tiny subtle details can be the difference between getting a diagnosis right or wrong. So it's no surprise that researchers have been trying to crack this nut for a while now. The big goal has always been to teach a computer to see the important features in a medical scan and then go find its twins. But a lot of past attempts have kind of hit a wall. So, what makes this new research different? How did they manage to get over those hurdles? Let's dive in.
Well, it really all comes down to finding the right balance. On one side, you had these really simple methods, like something called local binary pattern, or LBP. They were fast, sure, but they missed a ton of the fine, critical details. On the other extreme, you had these enormous deep learning models that were super powerful, but way too slow and resource hungry to ever be practical in a busy hospital. This new approach searches for that sweet spot, getting maximum accuracy without needing a supercomputer to run it.
The researchers behind this paper came up with what I like to call a dream team approach. So instead of betting everything on a single technique, they brilliantly combined 3 clever ideas into one process, where each step perfectly handles a specific part of the problem.
Here's how it works. First, the system describes the image by creating this super detailed digital fingerprint. Then, it refines that fingerprint, intelligently editing out all the noise and junk data. And finally, it classifies that clean, refined fingerprint and finds the best matches in the database. Let's break down each of these steps.
So for that first step, describing the image, the system uses 2 different programs working together, one called LDFP and the other LDLP. Think of them like 2 artists sketching a portrait. The first one, LDFP, is amazing at drawing the major shapes and big structural lines. The other artist, LDLP, is a master of all the subtle textures and fainter patterns. When you fuse their work together, you get a much richer, more complete picture of what's going on in the scan.
But that combined portrait is huge, and it's full of redundant information. That's where the smart editor comes in. It's an algorithm called moth flame optimization. And yes, it's actually inspired by how moths use the moon to fly in a straight line. In this system, the algorithm spirals through all the features in that digital fingerprint to find the brightest flames, the most important, most useful bits of information, and it just gets rid of the rest. Pretty cool, right?
And finally, we get to the judge. That refined, edited fingerprint gets fed into a really lightweight neural network for classification. And to find the best matches, it uses this special measurement called the Canberra distance. You can think of it like a special kind of ruler that's extra sensitive to tiny differences. Unlike other methods, it's perfect for spotting the subtle but absolutely critical details in medical scans.
Okay, so that's the theory. That's the whole dream team. But how does it actually perform when the rubber meets the road? Well, the researchers put it head-to-head against a bunch of existing methods, and honestly, the results are pretty darn compelling.
Just take a look at this chart. When we're talking about precision, which is basically how accurate the search results are, the proposed model hits 94.18%. That is a solid jump over the next best method and a massive leap over LBP, which remember is a really common technique used in this field.
Let's put a hard number on that improvement. We're talking about a jump in precision of a full 15.6% over that common LBP method.
Now, in the world of medical diagnostics, a 15.6% boost in finding the right image to compare against is a huge deal. That's the kind of leap that can take a tool from being just an interesting experiment to being a truly reliable co-pilot for a doctor. Every single percentage point of accuracy really matters.
And it's not just about the search. The classification part, that lightweight neural network also blows the competition out of the water. With an accuracy of almost 97%, it beats other standard machine learning models like random forest, KNN, and SVM by a pretty wide margin. This really shows that the entire system, from start to finish, is just incredibly effective.
So the numbers look great, they really do. But let's zoom out. What does all of this actually mean for the future of medicine? Because this isn't just some academic exercise. This technology has serious real-world implications for doctors and, of course, for patients.
What this research is really pointing to is a new kind of superpower for doctors. It's the ability to instantly consult millions of past cases, which can lead to faster, more confident diagnoses. I mean, just imagine being able to see how a similar condition progressed in hundreds of other patients to help plan the absolute best course of treatment. Ultimately, this is all about building a future where AI acts as a crucial partner, helping medical professionals save more lives.
And as the authors themselves put it, this isn't the end of the road, it's the foundation. This whole framework, combining smart description, optimization, and classification, it lays the groundwork for even more powerful systems down the line. Systems that are more scalable, more resistant to noisy or imperfect images, and even better integrated with deep learning. And that really leaves us with a fascinating question to think about. We've seen how this approach can completely change the game for image search, but what other medical mysteries could we solve if we just keep getting better at teaching computers how to truly see and understand the complex world of medical imaging? The possibilities? Well, they're just starting to unfold.